Yeah, continuing with 14.3. Another application that we can use multiple integrals for is actually a very broad mathematical concept called moments. And moments have uses in physics, in statistics, like hardcore. If you ever take a probability theory class, you'll be up to your nose in moments. Um, and basically anything that uses those ideas, right? So physics and engineering, statistics, anything based on statistics, all of them use this idea of moments. So what is a moment? A moment in mathematics is basically a number, a quantity, an amount that tells us certain characteristics about the graph of a particular function, right? And these can be important characteristics like where is the mode, like the highest y value? What is the rate at which the graph is doing this? Right. In statistics, where you have probability distributions, it can tell you a lot about the tails. For example, the one of the moments of a probability distribution is peakedness or kurtosis. It's the fourth moment, right? And that basically tells you like how sharply the tails, the distribution descends, right? Right, because if it descends more sharply, then your tails are going to be a lot narrower, meaning outliers are going to be a lot less likely. But that's a discussion for a statistics class. For us, just because just because we want something that is kind of easily observable, we're going to look at a physics application of moments. All right, so to start off with, we'll look at the idea that many real world objects do not have uniformly distributed mass. Some do, many don't. For example, um, is a good example. Yeah. For example, if I were to lift my laptop right now, depending on how I lift it, it might tilt backwards because a lot of the mass is distributed towards the back where the screen of my laptop is, right? Or even if I open a book, but I don't open it exactly in the middle, right? The side that has more pages on it is obviously going to be heavier. It's going to be denser, right? So when we talk about the density, that's really what we mean, is that not every part or every point on an object, two-dimensional or three-dimensional, is necessarily the same density. Or like think about plates even, like a fancy china. You'll have more weight distributed towards the middle of the plate, and the little edges that poke up generally are not as dense. But anyway, in that case where we don't have uniformly distributed weight or mass, we say that that's variable density. And a lot of times we can model that using what's called a density function. Right. So we typically are going to refer to density functions with the Greek letter rho, right? And when we get into spherical coordinates again, it's going to be interesting to not confuse the two, right? But anyway, in this case, for this assignment, right, rho means the density function. And essentially, by taking different kinds of integrals, we can get what are called the different moments of um, of the density function. So if I were to just straight up integrate with respect to both independent variables, x and y, then the result would give me the total mass, right? Taking just the straight up integral is what we would refer to as the zeroth moment. If I were to integrate x times this and y times this, I would end up getting the different components of the first moment. if I were to multiply my density function by x squared and y squared, I would get components of the second moment, right? So the idea is that we're integrating our density function multiplied by something, right? In this case, they would be your independent variables. Actually, in any case, they'd be your independent variables. All right, but since we're not multiplying by an x or a y, you can think of it as multiplying by x to the zero, right? And so then it makes sense why it would be the zeroth moment, right? So without further ado, let's look at an example of this in action. So we have the mass of a triangular lamina. So a lamina is essentially just a fancy math word that means a two-dimensional object. Think of it like a flat plane object that is heavier on one side than the other, right? So we're given the vertices of this triangular lamina. Okay, so if we were to plot those out, we have 0, 0, we have 0, 3, and we have 2, 3. So those make up the three vertices of our triangular plate. Okay. And essentially, we're given our density function. What it tells me is that as my x and my y get bigger, in this case, the output that I would get would be a larger density, right? Because if I plug in 2 and 3, I'm going to get a much bigger density than if I plug in 0 and 0. So with that said, as we move further away from the origin, we start to notice that the density increases. So if this were something I were trying to pick up off the ground, I would probably put one hand firmly under that really heavy part and another one over here where it's still pretty heavy so I can lift the rest. Well, I mean, that depends on a lot of other things, but that's just kind of to give you an idea of of how a non-uniform distribution might seem. All right. So we're given our density function. We want to know the mass. So we need to take basically the double integral over the region R of our density function 2x plus y dA. Okay, so remember dA, is a catch-all for dx dy or dy dx, depending on what order you put the bounds in. And I will say, there are actually several different ways that you could, well, two different ways that you can set this problem up, right? We can do a dx dy, or we can do a dy dx. What I do with that, or what I decide to do there, is going to dictate how I set the integral up. Because the way it's going to work out is whatever our inner integrand is, whatever the inner differential is, okay, we have to come up with a bound that is in terms of the other variable, right? So we can't just make the bounds 0 to 2 for x and 0 to 3 for y. That wouldn't work because then we'd be getting this entire rectangular region. We wouldn't be getting the triangular lamina. So with that said, I know that I can write the equation of this edge using what I know about lines. So we know that the slope of a line is given to us from our third grade math teacher, where we learned that it was rise over run, change in y over change in x. So this line has a slope of 3 over 2. So I could write the line in terms of x. Conversely, if I decided that I wanted to go the other way, I could also write this as x equals 2/3 y. Neither of these is particularly menacing, so it doesn't really matter which one we choose. Just remember, if I choose 3/2 x, which is the first thing we came up with, then my bounds are going to be from 0, that's the lower bound of x, to 3/2 x, or not x, blah, blah, blah. Actually, hold on a sec. Let's think about this a little more clearly. Okay. So if we decide to use y equals 3/2 x, okay, this is our y value. if you look at the y value for the region that we're trying to integrate over, the y value ranges from whatever the y value is on the line to 3. So 3 halves x would actually be your lower bound in that case, and 3 would be your upper bound. And then if I do it this way, remember 3 halves x and 3 are values of y. So this would end up being dy dx. Which means that my outermost integral symbol should have bounds that are values of x. And we know that the values of x range from 0 to 2, right? So whichever one I didn't use the equation of the line for, I can use the vertices for. So this is one way of doing that. When we calculate the mass, I'm going to save us some time and heartache here and just tell you what this works out to. Works out to 10. The integral itself isn't that bad. Just remember that when you do this inner part of it, you start off by doing your integral rules with the y's, but holding the x's constant. Then you plug in the top number minus plug in the bottom number, et cetera, et cetera. All right, so with that said, the other way, right, the whole reason I didn't want to just go through that process again is so I could talk about the other way to set it up. So this is one way, this is completely valid. I can totally do that. The other way would be using this version of that line. And in this case, that would be a bound of x. Now, if you look at the lamina, the x values range from 0 to whatever the x coordinate is on that line. So if I wanted to set this up the other way, my inner integral symbol would start from 0 and go up to 2/3 y. Right? And then we have our same function, 2x plus y. And then we have our outer bound, right? So again, 2/3 y and 0 are values of x. So dx should be our first differential. The other one, we can use just the values of y that are dictated to us by the vertices. So we would end up getting this setup. And if you were to work that out, you would also get 10. Right? So you would get the same answer no matter which way of doing it you choose, right? And now you've seen how both of them work and some of the things that you have to consider when you're choosing one method over the other, all right? So that is the 0th moment of the mass density function. If we want to move on to the first moment, the first moment, yeah, kitty. All right, but anyway, the first moment of the mass density function is related to the center of mass, right? And this is actually something that's parallel to what we would see in a statistics application as well. Because in statistics, if you have a probability density function, right, the first moment of that density function corresponds to the center or the mean, right? So measures of center based on the first moment. Center of mass is based on the first moment. Another thing to think about is when we talk about second moments, but I'm not going to get into that yet because we need to get through this example. So, moments, right, like I mentioned before, are just integrating your density function times a certain variable. One thing that you might notice that could potentially throw you off is that the component does not match the variable that we're multiplying by. Right, so the moment with respect to the x-axis, actually we multiply by y. And that's because the y coordinate tells us the distance from the x-axis. Right, and in a similar way, the y component of the first moment, we won't multiply by y, we'll multiply the density function by x. And again, that's because the x coordinate tells us the distance from the y axis, right? So it's a little topsy-turvy, but if you can remember that, they're switched, yeah, you'll get through the homework problems easily. So anyway, once we find those moments, those are what we would call the raw first moments, right? To get the actual center of mass, we would have to do a process called normalizing or standardizing. What was the word I used earlier? I used a word. Yeah, I don't remember. I lost it. But anyway, what we mean by standardizing or normalizing by a factor is basically taking into account the mass or the zeroth moment of your density function. So we would need to divide by the mass or divide each moment by the mass to get the center of mass, right? If you think about it, it kind of goes back to when we learn about mean in statistics, and you have to divide by the number of numbers, right? And um, and that would be equivalent to the zeroth moment of the probability distribution. Um, so that gives us the center of mass, right? Let's look at an example with that. So we want to find the center of mass of the lamina from the last example. So again, our center of mass is going to give us a coordinate, an x coordinate, and a y coordinate. So we are going to have to find the x and y components of the first moment separately. So to find the moment along the x-axis, we would take our double integral over the region R of y, remember that's the distance from the x-axis, times the density function rho. And dA, because the way that we set the bounds up is going to dictate how we write out our dy dx or dx dy, right? So if I choose the easier path, which was back here, where was it? Yeah, the easier path, which to me was the second one I showed you, we would have our bounds set up as the integral from 0 to 2y over 3, all right, of y times the density function, which was 2x plus y. And since 0 and 2y over 3 are values of x, we would integrate with respect to x first. Then the outside bounds are going to be values of y. And since we already took the line into account, the y values will just range from 0 to 3. So before I do anything, I need to distribute this y so that I can do my antiderivatives as easily and painlessly as possible. So if I distribute that y, I get 2xy plus y squared. And remember, with this order, we're starting with the dx integral. All right, so I'll go ahead and work through this one. So I have the integral from 0 to 3 of antiderivative of this with respect to x would be 2x squared y over 2, which would simplify to just x squared y, plus, we're not going to do anything with that because it's a constant, so we're going to just plop an x behind it or in front of it because multiplication is commutative. So we get xy squared for that one. And then we're going to evaluate that antiderivative from x equals 0 to x equals 2y over 3, and then integrate the result with respect to y. All right. And then from there, really should have left more space for this. All right, then from there, we're going to evaluate our endpoints. So I know if I plug 0 in for x, both of these terms are going to zero out. I only need to worry about 2y over 3. So if I square 2y over 3, I get 4y squared over 9. Remember, you square the coefficient. If you're squaring a fraction, you square both sides. All right, so 4y squared over 9, if I multiply that by a y, remember that only multiplies my numerator. So I end up getting 4y to the third over 9. And I should not forget the rest of my notation, because that would be silly. All right, and then substituting this x, I would multiply by y squared. That would give me 2y cubed over 3. And we have to integrate this with respect to y. Now, before I do that, though, I'll notice that both of these terms only have y to the power 3. So same variable, same power means they're like terms. I can combine them. I would need a common denominator, though. So multiply top and bottom of this one by 3. And we're adding 6 over 9. So this is really the integral from 0 to 3 of 10y cubed over 9 dy. Which, of course, I can take the 10/9 out. Then I can add 1 to the power, divide by the new power. So we get y to the 4th over 4. I'll go ahead and move the over 4 outside as well. We're going to evaluate from y equals 0 to y equals 3. So when I plug 0 in, that would give me 0. So I know that whatever this is, I'm just subtracting 0 from it. If I plug in 3, 3 to the 4, think about it as basically 3 squared squared, which is 81. So I would end up getting 10 that's still in the numerator from over here times 81 over 9 times 4. And lucky for me, I don't really need to multiply all of this out because all of this reduces. So 81 divided by 9 reduces to 9 over 1. 10 over 4 reduces to 5 over 2. So altogether, I get 5 times 9, that's 45. 1 times 2, that's 2. So this is the moment along the x-axis of mass, right? So when I divide this by the mass by 10, that gives me the x coordinate of the center of mass. Now we have to do the same thing for y to get the component along the y-axis, which will then allow us to get the y coordinate for the center of mass. So we know from the previous page that the first moment along the y-axis is going to be the double integral over the region R of x. Remember, that's your distance from the y-axis times the density function rho of x and y dA. All right, so if I stick with the same setup that I did for my bounds and my integrands to keep my life simple, all right, we end up with the following. So we have x times 2x plus y, and then this will be dx dy. And just like before, we would start by distributing the x. So we get 2x squared plus xy. Then we integrate with respect to x first. When I take the antiderivative of this with respect to x, treating y like it's a constant, I end up with, for the first term, 2x or 2/3 x cubed. For the second term, 1/2 x squared y. And we're going to evaluate that from x equals 0 to x equals 2y over 3, and then integrate with respect to y. All right, from there, I'm going to plug the values in. All right, so that's going to give me 4/9. Actually, no, that's not true. It's going to be 2 to the 4 over 3 to the 4. It'll be 16 over 81 times y to the third. All right. And for the second term, all right, we're going to get 4/9, 2/9 y cubed. Yep, that's right. All right. And then we're going to take the integral of that with respect to y. And just like before, we'll notice that we have the same variable to the same power, which means we can combine the like terms. So if I multiply top and bottom of this by 9, I end up with 18 over 81. If I add 16 and 18 together, I get 34 over 81, which I can pull out front. All right. And that simplifies the integral a bit. Now, if I were to take the antiderivative of y cubed, we know that we get y to the fourth. So we'll have this guy over here. We get y to the fourth over 4. Again, I can take the over 4 out front as well, so that I'm only evaluating y to the 4. And we're still going to evaluate from y equals 0 to y equals 3. When I do that, I have my 34. 3 to the 4 gives me 81, minus 0 keeps it at 81, divided by 81 times 4. And that's pretty convenient because the 81s just divide out. 34 and 4 are both even, so we know that that's going to simplify to 17 over 2. And that would actually give me the moment along the y-axis, 17 over 2. So if I want to find my center of mass, which we notate as x bar, y bar, I basically have to take my moment along the x-axis, which was 45 halves, divide that by 10, which means, in other words, I multiply the denominator by 10. So 45 over 20. Then I do the same with the moment along the y-axis. I get 17 over 20. I notice that the first one actually reduces, right? Both of these are multiples of 5. So that's going to be 9/4 for the x coordinate and 17 over 20 for the y coordinate. And that is our center of mass. So we calculated the first raw moment along each axis, x and y, and then we divided by the 0th moment to get our center of mass. Okay, now moving on to the second moment. So when we are starting off with the mass density function, rho, we know the 0th moment, i.e. just the integral, gives us the total mass of the object. We learned that the first moment can be used to find the center of mass. Oh, by the way, I flip back to this drawing here. 45, 9 over 4. Let's see, what is that? So it's 2.25. That doesn't make sense. Okay. Oh, I did it backwards. Maybe. Yeah, I did do it backwards. Whoops. So these are basically switched. Good thing we went back to look at that. All right. But yeah, when you write these coordinates out, it's not mx over m, it's actually my over m, because that's what's going to be in the x direction, or distance from the x-axis. That's right. No, x direction. Yeah. And yeah, so they're actually switched when you do center of mass. So the real center of mass would have been 17 over 20, comma 9/4. Now, if we go back to the lamina that we drew out here, 17/20 is 0.85, so that's a little bit less than 1. And 9/4 is 2 1/4, which would put us up here. So right there where I drew that big dot, right about, that is our center of mass, which makes sense because, like I said at the beginning, the density function suggests that if I get further away from the origin, the object gets heavier. So it makes sense that the center of mass would be shifted more towards the heavy side. Now, if it were a perfectly uniform mass density, then we would have got something that was exactly in the middle. All right. So anyway, getting back to our moment of inertia, after that little debacle there. Um, like I mentioned before, second moment, you're going to be multiplying your density function by each independent variable squared, right? And in statistics, this would correspond to, or at the very least, it would be related to your variance, right? Remember, that's the spread of the distribution. On average, how far away are the points from the center? So with moment of inertia, you can kind of think of it along the same lines. It's kind of an average about how far away we are from the center of mass, which kind of relates back to just the conceptual idea of what inertia is, right? Like if I'm taking a step and I'm meaning to go forward, it's different than if I were balancing in place, right? The center of mass would be at a different point. And the fact that I'm not moving would mean that on average, I'm staying pretty close to the center of mass, right? Um, but yeah, so again, the concept carries over and transcends areas of study. So that said, the second moment of rho is the moment of inertia. We can determine the x and y components using these formulas, okay? And summing these gives us what we call the polar moment of inertia. That's the moment of inertia about the z-axis. So if I have motion going on in the xy plane, there is some inertia in the z-plane. Like think about it, if you're stepping on a flat floor, every time you take a step, there is a vertical change, right? Now, some people might walk a little funny where they kind of prance around, and that's perfectly fine. They just have a higher polar moment of inertia. All right. So, for the next example, we want to find the polar moment of inertia for the lamina from the last two examples. So we're still using the same setup, right? But now the integrand is going to be different. So starting off with the x component, which will, oh, okay, there's a cat there. All right, so we're starting off with the x component. And this isn't going to be like center of mass where we're getting a coordinate because the question asks us to find the polar moment of inertia, meaning that we're going to find these two components separately, and then at the end, we're going to add them. That's all we have to do. Um, and we don't have to standardize or normalize with respect to anything either, which is pretty convenient. So anyway, getting on with it. This is going to be the double integral over the region R of y squared multiplied by the density function 2x plus y, right? dA. And I can still choose the same setup. I already know I'm going to have to distribute the y squared. So here are my bounds, 0 to 3 and 0 to 2y over 3. Distributing that y squared, my integrand is going to become 2xy squared plus y cubed. Since 0 and 2y over 3 are values of x, dx is my first differential, then dy. So when I go to evaluate this integral, I end up with the integral from 0 to 3 of x squared y squared. And for the second term, since y cubed is a constant, the antiderivative would be xy cubed. And we're going to evaluate that from x equals 0 to x equals 2y over 3, and then integrate with respect to y. So making my substitutions, my integral will now be 4 over 9 y to the 4 plus, and then 2/3 y to the 4. Love how this is following the same pattern pretty much all the way through. And of course, if we plug 0 in for x, both terms are 0, so that doesn't change the integrand. Now, combine like terms, just like we did in the other examples, right? So that's going to be equivalent to 6 over 9, which means that this will add to 10 over 9 times y to the 4. Then when I take my antiderivative, I can take out the 10 over 9. I know I'm going to get an over 5 from using my power rule for y to the 4. So I'm going to go ahead and just take that out too. Right? And at this point, I know that 10 over 5 reduces to 2 over 1. So this is really just 2/9. Next, I know that basically this is asking me to find 3 to the 5 over 9. Remember, 9 is 3 to the 2. So dividing the same base, we subtract the exponents. This will be equivalent to 3 cubed, also known as 27. So we got the component along the x-axis of 27. Now if I go and find the second one, and I'm working these because this one is actually not an example. The last two actually have not been examples in your textbook. Just me trying to simplify things. All right. So remember, just like before, we're using x to multiply the density function, x squared actually, because x tells us the distance from the y-axis, and this is the moment of inertia along the y-axis. All right, so we have x squared multiplied by our density function. All right, choosing the same setup, distributing the x squared. All right, then different anti-differentiating with respect to x, we would get 1/2 x to the 4th plus 1/3 x cubed y, evaluated from first bound to upper bound. Okay, and then plugging in the bounds will give us this integral. So 2 to the 4 would give me 16 divided by 2 gives me 8. 3 to the 4 is 81. Nope, not x. Y to the 4. All right, and then similar thing here. So that's going to be 2 cubed 8 over 3 cubed 27. If I multiply 27 by another 3, well, isn't that fun? All right, so these end up being the same value. So we're taking the integral from 0 to 3 of 16 over 81 times y to the 5th. Or no, not y to the 5th, y to the 4th. Getting ahead of myself. Okay. So we know that the antiderivative for this is going to be 16 over 81 times 5 times y to the 5th. We're going to evaluate from y equals 0 to 5, not 5, 3. All right, and we can actually use some similar thinking to get the numerical value for this. So 3 to the 5 divided by 81. 81, remember, is 3 to the 4. So 3 to the 5 over 3 to the 4, well, that's just 3. Yep. So we end up getting 16 times 3 over 5, which gives us 48 fifths. And that's going to be the moment of inertia along the y-axis. Now that we have the moment of inertia along each axis, we can find the polar moment of inertia by adding the two components that we already calculated. So we have 27, add 48 fifths. If I multiply 27 by 5, I get 100 plus 35, so 135. plus 48, which will give me 183. So 183 over 5. And that is the polar moment of inertia. Lots of spring in that step. All right. And then for this video, I'll do, I can get through the rest of the notes in this one. Okay, so one last example about moments. We're going to extend this to a three-dimensional problem. Okay, so we want to find the center of mass of the unit cube. That just means a cube whose side lengths are all 1, which has a vertex at the origin. So that kind of gives us a choice on how we orient the cube. Because I want to keep things simple, I'm going to keep the cube in the first octant. Okay, so all of these side lengths are 1. That makes it a unit cube. All right, so we want to know center of mass. Before I can get the center of mass, I have to know what the mass is. Remember, that's your 0th moment of the density function, i.e. just the double integral. Actually, triple integral. Yep, that's right. It's a triple integral. All right, so the triple integral over the region Q, which is typically the letter that we use for triple integrals as opposed to R for double. It's just how your textbook does it. Essentially, we're just integrating rho xyz dv, right? Going back to that whole volume idea. Instead of dA, it's dv because we're doing a triple integral. And again, that's just a way for us to ambiguously say dx, dy, dz without assigning an order. So if I try and set up my bounds here, because this is a unit cube, and it's not like that triangular lamina where we're in danger if we try to just use the coordinates we were given, right? We could actually just have our bounds for every variable be 0 to 1. Because think about it, x is 0 to 1, y is 0, or x is 0 to 1, y is 0 to 1. That makes the square base of the cube. And z is 0 to 1, that fills up the cube. All right. So there's nothing wrong with me going integral from 0 to 1, integral from 0 to 1, integral from 0 to 1. K is a constant, so it can go out front. Other than that, rho is x squared plus y squared plus z squared. And because the bounds are all the same, it really doesn't matter what order I put my differentials in. So starting with our innermost integral, we're integrating with respect to x first. That's going to give me 1/3 x cubed plus xy squared plus xz squared. We're going to evaluate that from x equals 0 to x equals 1, and then the result of that will be integrated with respect to y, then with respect to z. Yeah, I'm not going to have space on this one either. All right. So when I plug my numbers in, remember these are only being substituted to x. The other variables are going to stay put. We end up getting 1/3 plus y squared plus z squared. So this is going to be the double integral. Each set of bounds is 0 to 1. Integrand will be 1/3 plus y squared plus z squared. And there's the differentials. And we can take the antiderivative with respect to y now, which is going to end up giving us the same thing. So I'm going to skip a couple steps to save myself some space here. And I know that this is going to end up also giving me 1/3 plus 1/3, so 2/3, plus z squared, dz. And if I were to add, yeah, and if I were to add, what am I talking about here? Oh, yeah. If I were to go ahead and do it, if I were, it's late, y'all. If I were gonna take the antiderivative with respect to z now, okay, I would end up getting 2/3 z plus 1/3 z cubed. And we're gonna evaluate that from z equals 0 to z equals 1. And of course, this is gonna give me 2/3 plus 1/3, which is 1. Wow, the unit cube has a mass of 1, 2. Crazy. All right. So now that we know the mass, we can actually go and find our center of mass. All right. So to do that, look at that, convenient. I have a notebook right here. So to do that, we have to find our different first moments. So you're going to have, all right, you're going to have the moment along, and instead of axes. So here's kind of a weird thing that happens. Because we're now looking at a function of three variables. Three, yeah. Because we're now looking at a function of three variables. Instead of looking at moments or moments along an axis, we're looking at moments along a plane. Okay? And that's because now we are looking at three variables instead of two. So we're going to have our moment along the XY plane. We're going to have a moment along the XZ plane. We're going to have a moment along the YZ plane. And it works really similar to how moments did with two variables, right? So we're still going to be doing triple integral over the region Q. This time, though, Z is the variable that is not there. So that's what I'm going to multiply rho by. All right. And then for XZ, so our moment along the XZ plane, still a triple integral over the region Q. This time Y is the variable that's missing, so that's what I'm going to multiply rho by. And lastly, X is the one that's missing here, so I'm going to multiply rho times X. And these will give me my raw first moments of the mass density function, which I can then divide by the mass, which in this case turned out to be 1, and that'll give me the individual coordinates for the all right, and that'll give us the individual coordinates for the center of mass of the unit cube. If I had to guess, I would probably say that it's in the center. But we'll carry out our computation and we'll see if I'm right. Okay, so getting the actual setup. Moment along the XY plane, we can use the same setup for our integrand. Very convenient that all of our bounds were 0 to 1. All right, K again is still a constant. Oh my God, did I drop that? I sure did. That's hilarious. Okay, all. So it turns out the mass isn't actually 1. The mass is actually K. There we go. Yep. So whatever this constant of proportionality is, right, that would end up being the mass for the unit cube. Okay. So anyway, getting back to this, let's hope I don't make the same silly. All right, we're going to take our integrand to be z multiplied by the density function x squared plus y squared plus z squared. Right, and here it could be prudent to save z for last. In all honesty, you can kind of just try mixing them up and see what happens. It's not really going to make that big of a difference computationally. So This time, remember we're distributing that z to all of these terms. So this becomes x squared z. This becomes y squared z. This becomes z cubed. And that's going to affect how the integrals turn out. So innermost, right, we're differentiate or anti-differentiating with respect to x. So I end up getting 1/3 x cubed z from that first term. This doesn't have an x, so the antiderivative will be x y squared z. This doesn't have an x, so the antiderivative will be x z cubed. And of course, we're going to evaluate that from x equals 0 to x equals 1. When I do that, my integrand is going to become 1/3 z plus y squared z plus z to the third. And now I go to the second integral where I take the integral with respect to y. Okay, so for the first term, that doesn't involve y. So 1/3 yz. Second one, 1/3 y cubed z. Third one, that doesn't involve y. So the antiderivative will be yz cubed. And we're going to evaluate that from y equals 0 to y equals 1, and then integrate with respect to z. So then when I do that, remember we're plugging these numbers in for y. So the result is going to be 1/3 z plus 1/3 z plus z to the third. If I combine like terms, I can actually simplify this a bit and call this term 2/3 z. Now when I take the antiderivative of this with respect to z, it's a little more straightforward. So my antiderivative, we're going to get 2/3 z squared over 2. Little math will tell me that's 1/3 z squared plus 1/4 z to the 4. And again, we're going to evaluate this from z equals 0 to z equals 1, which will result in 1/3 plus 1/4 times k. Right, and if you add 4/12 plus 3/12, you get 7/12. So 7/12 k is going to be my moment along the xy plane. And if I divide that by the mass k, then I get 7/12 as um, the z coordinate for the center of mass. Right, so a way to remember that is whatever you multiplied rho by, that's the coordinate that you're going to get with it. Right. So then, next one. Oh, man. Okay. Next one, we have the moment along the xz plane. And it's going to work out in a really similar way. All right, so this is going to be k times this basically same setup. Except this time we're multiplying by y. So if I distribute the y to each of the terms, I would get x squared y plus y cubed plus yz squared. And for fun, let's keep the differentials in the same order just to see what happens, to spice up our lives a little bit. All right. So taking the first integral, we end up getting 1/3 x cubed y plus xy cubed plus xyz squared. And we're going to evaluate that from x equals 0 to 1, and then follow through with the following integrations. So the integrand is going to become 1/3 y plus y cubed plus yz squared. Now when I go to take the second integral, the antiderivative I get will be 1/6 y squared, right? Dividing by 2 is how I got the 6, plus 1/4 y to the 4, plus 1/2 y squared z squared. We're evaluating that from y equals 0 to y equals 1, and then integrate with respect to z. So then, if I plug my numbers in, I end up getting 1/6 plus 1/4, right? This would be 2 over 12 plus 3 over 12. So that gives me 5/12 plus 1/2 z squared. All right, and then when I take this antiderivative, we get 5/12 z plus 1/6 z cubed, and we're evaluating from z equals 0 to z equals 1. And at this point, um, oh yeah, we end up getting k multiplied by 5/12 plus 1/6. 1/6 incidentally is 2/12, which results in, what do you know, 7/12 k. So if we were to do the same thing with the moment along the xy plane, right? Did we already do xy? We did already do xy. So if we were to do the same calculation for the moment along the YZ plane, I'm going to spare you the details because you can work it out yourself at this point, I hope. And you'll end up getting the same thing. So if I wanted to get the center of mass, this time it would be x bar, y bar, z bar. I would get the moment along the xy plane, which was 7/12 k divided by the mass. So I'll write it out this time, divided by k. And similar thing with the y coordinate, and similar thing with the z coordinate. Since the k's will divide because they're a constant that is presumably non-zero, we end up getting that our center of mass is 7/12, 7/12, 7/12. So is that the middle of the cube? Hmm. Hmm. Well, it's not 1/2, 1/2, 1/2, but it is pretty close. I'd say it makes sense. So that's the center of mass, and that is all I'm going to say about moments. So to kind of recap what I said about moments. Remember, moments are quantities that give us information about the shape of a function's graph. That can be, in the case we looked at, where the graph represents an actual shape in space or even in the plane. And you can get things like the mass, the center of mass, the moment of inertia, and a whole bunch of other things that you will learn about if you ever have to take a mechanics course. Okay. Um, we learned that you can compute moments by multiplying your density function by different variables, right? Remember, the variable that you multiply by gives you the coordinate for the center, that you get from the first moment. Um, Other than that, it's just really understanding how there are parallels and patterns here and how you can kind of extend these things from one field of study to the other. And that's one of the cool things about math is that if you understand the mathematical definition of something, it's a lot easier for you to make jumps between different fields of study. All right. So with that said, we're going to go to the last topic for this little tidbit of a section, surface area. So surface area, I want us to think back to something that I said when we were looking at moments. Remember when we made the jump from from two variable to three variable functions? What was the difference when we went to calculate the first moment? Remember, it was rather than being along a line or an axis, we were along a plane. Now I want us to take that thought process and apply it to arc length. When we learned about functions of a single variable in Cal 1 and Cal 2, you learned how you could find arc length, which is basically like if I were to chop a piece of a curve and measure the length. The thing is, for a single variable function where the graph is just a two-dimensional curve, if I chop any piece, that piece is going to be just a line, similar to how moments are taken along an axis, two variables. When we extend to surfaces in three-dimensional space, a little snippet of the surface would not be a line, it would actually be a little patch, right? Been watching Criminal Minds, so my mind went to a really gross place when I wrote that out. Um, but the idea is that you're taking a plane as the chunk instead of a line as the chunk. Similar to how with moments, you were taking the moment along a plane as opposed to along a line. Now, let's think about something. If I were to take really small arc lengths and add them together, that would give me the length or the arc length of a bigger piece of the curve, or perhaps the entire curve if it's graphed on a closed interval. With three-dimensional space, think about what happens if I were to chop off a little patch. I wouldn't be measuring the length of that patch. I would be measuring the area of that patch because it's basically like a little rectangle. If I were to do that with a bunch of patches that are consecutive and then add all of those together, I get the surface area of a region or even the entire surface. So the way that we approach calculating surface area using double integrals is really similar in the setup to how we would calculate arc length using functions of one variable. So to remind you, that's the formula for arc length for functions of one variable. If we extend this to a function of two variables whose graph is a three-dimensional surface, we now have partial derivatives instead of just f prime. So really you're just taking the double integral of the square root of 1 plus fx squared plus fy squared dA. And again, remember dA is just a way for us to ambiguously say dx, dy in any order. So let's look at an example. We want to find the surface area of the portion of the plane given by that function that lies above the circle x squared plus y squared is less than or equal to 1 in the first quadrant. All right, and then we're given a hint. We can simplify this to a number times the area of the base region. Ooh, intriguing. So first off, this is my base region, right? So this is the base. This is what we use for R, right? This is what we use to figure out bounds and the like. Another thing to keep in mind when we are setting up the bounds is that we're only looking at a piece of that circle, not the entire thing. So we're only interested in parts that are in the first quadrant. Now that said, to get the setup for my integrand, I'm going to need some partial derivatives. So I'm going to take the partial derivative of z with respect to x, right? 0, -1, 0. Okay. Then I'm going to take the partial derivative of z with respect to y. 0, 0, -1. So in this case, what ends up happening is our surface area is the double integral over the region R of the square root of 1 plus -1 squared plus -1 squared dA. Well, you know what's kind of cool there is that this works out to just the square root of 3, which is a constant. So really, with this one, we just have the square root of 3 multiplied by the double integral over the region R dA. Well, you know what, guys and gals and theys? What is that? That's the area. Yep, that's the area. And what shape is that? It's a circle. Technically, it's a quarter of a circle. You know, a formula for that, you know? Right, the area of a circle, the entire circle, would be pi r squared. If you were to look at this, the radius would be the square root of 1. So the area of the entire circle would just be pi. If we take into account that we're only looking at the part that's in the first quadrant, we know that this would end up being the square root of 3, that constant we took out, multiplied by pi over 4, right? The area of the circle divided by 4, because we're only looking at a quarter of the circle. So this simplifies that problem greatly and makes it so that that's our surface area. Pi times the square root of 3 all over 4, which does have a decimal value, but TBH IDC. All right. But anyway, that's surface area. So it's essentially an extension of what you learned about arc length in Cal 2, right? So now instead of just the square root of 1 plus f prime squared dx, it's double integral over the region R of the square root of 1 plus, instead of f prime, the partial derivatives squared, dA instead of dx, right? Because we have to integrate with respect to both independent variables. And yep, that's about it. Happy mathing, y'all.